So folks, the homework that was due today was graphing linear systems. For those of you coming from a different curriculum other than American curriculum, you might have called these simultaneous equations. Regardless of what you called it, we are going to call it systems of linear equations. And the first task that I had you guys do with this was to graph. Anytime that you graph any equation, you have to have that equation in slope-intercept form. Also, anytime that you graph an equation, you want to make sure that all of the information that you need to read from it can be seen within the window. So I'm going to show you guys how to set up this problem and solve this system by elimination. The first thing that you want to do is write your system side by side as I'm demonstrating so that you can work out any work below it and the work between both of them doesn't interrupt. So let's put this into slope-intercept form. Now notice when I'm dividing by the 4 here, I'm showing every single term gets divided by the 4, by -4. And the reason why I do that is because it prevents from a lot of computational errors happening. Most people can do the first one in their head every single time correctly, but the second one kind of gets like the negatives get dropped out or put back in, something like that. And so I highly suggest that you divide everything by the coefficient of y when you're putting this into slope-intercept form. Now, this one, we're not going to be afraid of the fractions that result from the slope-intercept form. We are going to show that every single term gets divided by this -5 here. Now, let's see what this looks like on the calculator. So, after you've put the 2 equations into your calculator, it should be something like this. 1/2 x minus 3, 3/5 x minus 8/5. Next, you're going to want to graph it, and the reason why you want to graph it is for this particular problem, notice that the intersection is not really in the window. If it's that close to the edge, it could be within the window. It's kind of hard to tell. And so what you want to do is you want to change your window so that you can actually see the intersection. So I'm going to decrease both the y min and the x min so that when I graph it, again, the intersection is clear. Oh, I'm going to do that one. I'm going to actually do this as -20 as well. Now, when I graph it, the intersection is clearly within the window. You can see them right there. Now, I'm going to draw the graph that is on my calculator. Just a quick sketch, nothing fancy, okay? Trying to make it look as accurate as possible. Ooh. This is a little bit more difficult than I thought it was going to be. This is really close to 0, but not quite. Okay. All right, well, that's not the prettiest, but at least your solution looks like it should be in the right spot. So go ahead and put in a coordinate where that solution should be. We'll be able to actually label it with an ordered pair in just a moment. Now you're going to be using the calculate menu, which is above the trace button. It's in blue, which means you put second trace. That gives you the calculate menu. That calculates everything that's that calculates everything from the equations that are in your y equals. Hit 5 for intersect. And your calculator is going to ask you a few questions. First curve. That just means is the line that the cursor that's blinking on the y1 function, and yes it is. Second curve, is the cursor that the line is blinking on, is that the y2 function? Yes. So hit enter when you mean yes. And this time your calculator is asking you, can I guess the intersection that is closer to the blinking cursor? And you say, yes. And we have our intersection. Now, our intersection here is our solution for the system. Now, if everything goes right in the two other ways that we solve using elimination and substitution, we should be getting this solution for every single one. And on your homework, that's what you should be looking for. When you graph, or when you use elimination, or when you use substitution, if you're using two different methods for one system, you should be getting the same solution for both. Makes sense, right? Now, elimination. Elimination is also called linear combination. Again, I'm going to write out my my equations side by side so that it's easier to show all my work and solve, and I don't get confused between the work of each one. Next, I have to decide which variable am I going to solve for. Now, in this particular situation, there's not a clear one. The coefficients of these two are different. The coefficients of these two are different. So I'm just going to solve for the x. Simply because they're smaller numbers, I only have to multiply this one by 3 and then multiply that one by 2. And the reason why I do that, think of lowest common multiple between the two coefficients that you're going to be solving for. The reason why you want to do that is that if I make the coefficient of x opposite, as in one's 6 and one's -6, then they're going to cancel out and be eliminated. So I'm going to multiply this one by 3. I'm going to multiply this one by 2. And then I'm going to combine them with subtraction. Now, notice 6x, 6x. I've just rewritten both of the equations so that they have the same coefficient of x. Now notice what happens when I subtract this equation from this equation. X is eliminated. And we have -12y minus 10y, which is going to give us a -2y. And we have 36 minus 16, which is going to give us a 20. And la-ti-da, what do we have here? Y equals -10, which is the exact thing that we got when we graphed. Whoa. Okay, hold on now. Don't get too excited yet. We're not done with the problem yet. We got to make it through. Now that we have what y is equal to, we now have to find out what x is equal to. So now I'm going to take my original equation and I'm going to substitute in -10 instead of y. And well, we get -14. Finally, write your solution as an ordered pair using the x coordinate first. Using the x value first. We want to always refer back to the equation and remember that the solution to a system is when the two lines of the graphs intersect. Substitution. Now for substitution, you're going to have to solve for one variable in terms of the other. So now, since these coefficients are all divisible by 2, I can actually divide this one, or multiply by 1/2, and I get that x minus 2y is equal to 6. Then I can add 2y on both sides, and x is equal to 6 plus 2y. Now I'm going to take my other equation, and instead of writing x, I'm going to write what I just used to solve for x. Now x is actually 6 plus 2y. I'm just going to substitute it in there, and that's why it's called substitution. Solve for one variable, substitute in. It's kind of like you're still eliminating, but you're actually replacing, and that's why the x is no longer in this equation. Now, combine like terms. Subtract 18 on both sides, and you get that y is equal to -10. Much like what we did last time, we're going to take the value of y, and we're going to substitute it in for y in our original equation. In the other equation that we solved for x. Since we already have it solved for, we can easily evaluate. 6 minus 20, -14. Again, write your solution as an ordered pair. Go ahead and check out the next 3-minute, very short video on how to deal with systems that have no solutions or infinitely many. I'm going to show you what it looks like algebraically.